Okay, so we're transitioning between monohybrid crosses and dihybrid crosses, and we'll do multi-hybrid crosses later, but dihybrid being that we use two traits at the same time and look for their results. And to help explain how we're going to do that, how we're going to figure out the ratios and things we need, I want you to take a very short side trip and talk about the probability of multiple events occurring. Okay? In the most simple way we can, we're going to talk about the product rule, because that's the one we're going to use for this process. All right. So basically, we're asking, what's the chance of something happen? Okay. In genetics, we like to know the likelihood this occurs. For example, if you cross two heterozygous individuals, what's the probability that one of their children will be recessive or whatever? Okay, when it's used constantly in things like genetic counseling and things where we know, look at the individuals who try to figure it out. So it's basic probability. Okay, and we know that if we cross two heterozygotes, that about 1/4 of the progeny, we don't know which one it's going to be, child 1, 2, 3, or 4, but we know that 1/4 ought to be recessive on average, and that about 3/4 ought to show what the dominant has. Okay, so that's just dealing with probability. Now, what we're doing now is we're moving to a situation where we've got not just one trait, but two traits. So what's the probability of this happening with this at the same time, simultaneously? And probably the easiest way to sort of illustrate it is maybe using families, okay? What's the chance of things happening together? Fortunately, they're very simple rules to help for us to figure it out. Now, the rules can get complicated in a moment, but for right now, we're going to use very simple rules, and that's all you need to work these dihybrid and multi-hybrid problems, all the way up through epistasis and everything else, okay? So, a little simple example. A family has 4 children, or is going to have 4 children or something. What's the probability that they're all one sex or the other? That they're all male or they're all female? In this case, I ask, what's the chance that they're all girls? Okay, so we need some information, and this is really critical information. Okay, the first is I need to know the probability of any one child being something. Okay, in the case we used before, we had 3-to-1 ratios, right? So I need to know the probability there. We're making a much simpler case here. The base probability of producing a boy or a girl, if you're a human, is 50-50. Okay, there's a 50-50 chance because the way the genes are set up, you've got 2 X's in a female and you've got an X and a Y in a male, so you're essentially crossing a homozygote times a het, if you think about it that way. Always gives me a 1-to-1, right? Okay, so my 1-to-1 outcome is what I expect. About 50% are going to be male, about 50% are going to be female. And it turns out in the real world, there's all sorts of little things that can happen to drive it toward more males or more females, but the primary ratio, called the primary sex ratio, in humans is 1-to-1, 50%. All right, second thing is very important. The genders are independent, right? Whatever you are, male or female, and if you have a brother or sister that was before or after you, let's just say they were next in line, parents had another child. It didn't matter what you were, male or female, that child's chance of being a male and female is 50-50. It's not predicated on you, okay? It's not Bayesian probability. We're just going to say they're independent events, independent reproductions, completely independent. If that rule holds, then we've got some things that happen here. And that rule is going to hold for our genetics problems for now, okay? So it's very important. All right, so what's the probability of having 4 daughters out of a group of 4? How often are we going to see a family of 4 walking along when all 4 of them are girls, right? And we think about it, okay, each child has a 50-50 chance of being female. The probability of the first child is 50%, probability of the second child is 50%, third child 50%, fourth child 50%. First and fourth are independent. It could have just as easily been a boy the first time and a girl the fourth time. This is 50-50, okay? All right? So what we're allowed to do is we're allowed to multiply those events together. Just simple multiplication. It's known as the product rule. It's also known as the multiplication rule. Okay? Product rule, multiplication rule. You simply multiply them out. Right? Probabilities don't change. And that's really important because it's important that the first event and every event be independent. People that I know, gamblers, it's called the gambler's fallacy. If you've ever been to a casino or something or ever go, you'll see people sitting there at the slot machine or whatever they're doing, putting their money in, poking, or the roulette wheel, and they're just going, okay, this thing is not paid off. I've put in $20. It hasn't paid off. It's going to pay off. Next one's going to pay off. Next one's going to pay off. It's not going to do that necessarily because it's independent event. Okay, it's as independent as they can make a computer randomization process be. But this idea that somehow after 40 tries, okay, or it says on here it pays 1 in 100, and I've put in 99, it's going to pay the next time. It's independent, right? That's called the gambler's fallacy. Well, in this case, every event's independent, and so we can multiply them out. It's very handy. Okay, we've got this nice outcome. In this case, 1 in 16 families ought to be all girls. You got a 1 in 16 chance, essentially. Okay, if you produce 4 children, you got 1 in 16 chance that they're all going to be female or they're all going to be male. Okay? That's what the product rule says. You just multiply them out. 1 in 16 is what you get. It's all based on these multiplication systems. Just simple multiplication out. 1/2 times 1/2 times 1/2 times 1/2. You keep going on. You want to know what the probability of having 10 children and they're all girls. You do this. Okay. All right. Now, it gets more complicated, as most of you know, if taking probability. If I ask the question, I've got 2 girls, what's the chance that the next 2 are girls? That's a different probability problem, okay? We're not dealing with that. Or if I've got 1 boy, what's the probability that the other 3 are girls, okay? Those are different higher level probability issues we're not going to worry about. Your book tries to do, or most books do, a few of those problems. Don't worry about them. Just worry about a simple problem. I know the probability of this is 1/4. Probability of that is 3/4. I want to know the joint probability. I can multiply any of those 2 fractions or numbers together, okay, through the multiplication rule. So we're going to call it the product rule. And the probability of 2 or more outcomes is, if assuming that they are independent, is just the product of their independent probabilities. I know this occurs 1/4 of the time and that occurs 1/16 of the time. What's the probability of them happening together is 1/4 times 1/16, or whatever number you need, okay? And that's important because all you're going to do now is take the middle big 6 outcomes, the predicted outcomes of 1/4 or 1/2 or 1/3 or whatever it is, and you're going to multiply it times the other probability from the other cross, and that's going to give us our joint probabilities. It's going to be a lot simpler than doing these things, where you try to do these big old Punnett squares where you get up and you have to do all this stuff and figure it out. It takes you forever to do. That's big A, little a, big B, and you fill it all in. Those are fine. Do that, but I'm going to show you a way using the product rule that we don't have to do that, and you can get to the answer very quickly.